Welcome to lecture 4 of module 3 on heat transfer.
This lecture will be on graphical solution of unsteady state heat conduction problem. Okay. This is in continuation to our previous lectures on unsteady state heat conduction. In fact, in last few lectures we have discussed on various types of heat conduction problems. One is on lumped parameter model, another is distributed parameter model, and for both the cases we tried to find out the basic governing equation, and then we have solved those governing equations with the help of analytical methods. So, analytical solutions are available for those kind of problems, but analytical solution is not always available. It is because of the complexity of the problems. When there are problems are a bit complex, okay, the analytical solution may fail. Analytical solution is difficult to get an analytical solution for such complicated problems, or when the equation is very complicated, the analytical solution might be very complicated also. So, therefore, another method by which we can find out the solution of unsteady state heat conduction problem is by graphical method. In fact, here what we are going to demonstrate is that for unsteady state problems in convection environment, when the heat transfer is taking place in convection environment, for that type of situations there are as we have seen, there could be some analytical solution. So, that expressions which are very complicated, which are very weak expressions for that, and getting the values, extracting the values depending upon the problems from those equations sometimes become laborious, sometimes become exhaustive task. So, what can be done? Those things are being computed and presented in the form of charts, and with the help of these charts one can quickly find out the solution of the problems. So, in this lecture we are going to discuss how to take care of the charts, how to use the charts to find out the solutions for different geometries. And to tell about these charts, we know that there are three basic type of configurations, like Cartesian coordinate, cylindrical coordinate, and spherical coordinate systems. So, for Cartesian coordinate or flat plate, for cylindrical coordinates, or for cylinders, and for spheres, for three different type of geometries of the bodies have been considered for developing the charts. So, charts are available for infinite plane wall of thickness 2L, then long cylinder of radius R0, and sphere of radius R0. So, these are the three cases for which the charts are available to find out the solution of the problems. Now, what are the solution for these cases we can find out? First thing is that from this chart we can find out the center line temperature So, there is a plot that says that center line temperature, dimensionless center line temperature, say T naught by T I bar versus Fourier number. So, T naught bar or T I bar, or T naught bar is equal to say T naught minus T infinity. This T infinity is the environmental condition. Temperature condition. So, from the body the heat is being transferred to the environment. So, T naught is the temperature at the center, 0 indicates that at the center point, and T I bar is T I minus T infinity, where T I is the temperature at the initial condition of the body. So, we can say that T I and T O are initial and center line temperature of the body of concern. That means, we can find out from the figure that T naught bar versus T I, sorry, T naught bar by T I bar versus Fourier number plot, which is basically it is a dimensionless, both are dimensionless quantity. This is called T naught bar by T I bar is the dimensionless center line temperature, and F O is again a dimensionless quantity. This is called Fourier number, and these variations are being there for various values of one by Biot number. So, for various values of Biot number or 1 by Biot number, the center line temperature plots are available, and for all the three geometries, or for flat plate or cylinders, long cylinders or spheres. So, we can see from this figure that how the charts are, or that lines are being drawn for various values of 1 by Biot number. The figure says that is the variation of T naught bar by T I bar with Fourier number, and you can see that there are different scales, being kept. So, to accommodate a large range of values of the Fourier numbers as well as and the Biot number variations. To take care of those things, different scales are being merged here to give some concrete values on dimensionless center line temperature for an infinite plane wall of thickness 2L. Exactly similar way, we can see that this is the center line temperature case plot for infinite cylinder of radius R naught, and here we can see that the Biot number is 1 k by h o, 1 by Biot number is k by h o. So, Biot number is based on the radius of the cylinder, and the plot is the center line dimensionless center line temperature T naught bar by T I bar versus Fourier number. This plot is there, and then similarly we have for sphere also there is another similar kind of plot, dimensionless center line temperature here, again the same thing, and this is also that 1 by Biot number variation of the 1 by Biot number. Here also the Biot number is defined as H L by k, which is nothing but h into radius of sphere by the thermal conductivity, which is in the inverse of this k by 1 by Biot number is k by h into R naught. So, like this way we have got this center line temperature, dimensionless center line temperature we can find out from the expressions for any problem being given for one particular geometry, we have to concentrate on this chart, we have to calculate the values of Fourier number, we have to calculate the value of 1 by Bayes number, and then from there we can find out the values of center line temperature. But why we want to find out the center line temperature? The reason is that there is another plot we can find out which takes care of the value of any local temperature which with respect to the and that plot will see what is happening in the next plot, that is it is being done like this, that any local temperature is also calculated. That is also a dimensionless temperature. It is like that, there will be a plot of T this versus 1 by Bayes. So, we can understand why in the very first case we need to find out the center line temperature, because once we know the value of center line temperature, then from the center line temperature expressions we can find out our values, we can find out that dimensional reduced temperature at any location. So, in this the second chart, this is the chart 1, okay, and this is chart 2. In the second chart, we can find out that it is a dimensionless local temperature versus 1 by Bayes number, and this plot is for various dimensionless values of, say, in case of x by L for plate, flat plate, for flat plate, and then we have say x by R naught for cylinder, and similarly x by R naught for sphere. So, this is the variable with respect to these different values of these x by L or x by R naught or x by R naught for different cases. We have the plot dimensionless temperature, local temperature versus 1 by Bayes number. So, all the plots are dimensionless plots. So, if you see here, this plot, it says for the flat plate or the plane wall of thickness 2L, we can, if we set thickness 2L, then the Bayes number is becoming x by L, it is becoming x by L, and we have this dimensionless local temperature versus 1 by Bayes number plot is there, and from the plots we can find out the values of any local temperature that can be calculated. Similarly, we have the plots for any cylinder where x is equal to is nothing but r and r naught is its radius. So, x by r naught is nothing but r by r naught, and there is a plot of local dimensionless local temperature versus 1 by Bayes number. Okay. Similarly, for the cylinder also there is similar kind of plot where we have dimensionless local temperature versus again r by r naught. So, x is equal to r here for the sphere. So, if we go back again, that here actually x is equal to r and x is equal to r. Okay. Similarly, the third chart, there is another chart. So, that takes care of the heat flow. How much is the heat flow that has happened for a particular time, that can be calculated from that figure, from the chart, and it says it is a plot of q versus q by qi versus Fourier into Bayes square for various Bayes number. So, Bayes number is the variable quantity, and the x axis is that Fourier into Bayes square, which is nothing but h square alpha t by k square. So, this is the x axis and this is the y axis is q by q naught qi. So, what is this q? Q is actual heat loss by the body in time t, and qi is initial internal energy of the body, and that is equal to rho into Cp into V is the volume. So, rho Cp V is the mCp, rho into V is the mass, into Cp is the mCp into Ti bar. Ti bar means that is, so it is the reference temperature with respect to the environmental temperature, that is T infinity. So, Qi is the initial internal energy of the body with respect to the environmental conditions, and Q is the actual heat lost by the body. So, this is again the y axis is the ratio of two dimensionless quantity Q by Qy. So, a plot of Q by Qy versus this Fourier into Biot square for various values of Biot number will give us an idea what is the heat flow for a certain time duration, where we know the values of Qy for the different substances, different material bodies, and if we see that the plots here, yes. So, you can see that Q by Qy versus Biot square into Fourier for different values of Biot number, the plot is again we can see it is a semi-log plot for plane wall. Similarly, we can have the semi-log plot for Q by Qi versus Biot square into Fourier number in case of an infinite cylinder, and also we have a similar kind of plot for Q by Qi versus Biot square into Fourier number in case of a sphere of radius I, and it is for different values of various values of the increasing values of the Biot number. Okay. Now, what we will do is we will take up a problem, and that similar problem will be applied to all the few geometries, and we will see that what happens to the center line temperature, what happens to the heat flow rate from this. We will go through a problem, we will try to demonstrate it with the help of a problem. Okay. So, problem 1, if we say the question 1, it says that a large aluminum plate, a large aluminum plate of thickness 4 centimeter, okay, and initially at 400 degree centigrade is suddenly exposed to the convection environment of 30 degree centigrade, okay, with heat transfer coefficient of 500 watt per meter square per Kelvin. Okay. For aluminum, K is equal to thermal conductivity is equal to 215 watt per meter per Kelvin, then rho equals to 2700 kg per meter cube, and Cp equals to 900 joule per kg per Kelvin. Okay. So, the target is to calculate the center line temperature after 1 minute. This is the first part. B, the temperature at 0.8 centimeter from one phase after 1 minute, and the third part is the heat loss per unit area from this plate during this time, that means 1 minute. Okay. So, this is the question. The problem states that we have a flat plate, okay, of this kind. Say this is a flat plate, but this is of thickness 2L, and say if this is the center line. So, here x is equal to 0 and say this is x along x direction. So, heat is being conducted in this side and this side from both the surfaces, okay. And according to our definitions and all, this is T infinity, and at the beginning it was the surface temperature is T I, okay, that is the initial conditions that we have seen in previous cases, and this temperature at this point is the center line temperature, which is nothing but TO. So, what we have to find out is, first we have to find out the values of TO, and then we have to find out that is the center line, and then we have to find out that according to the problem part B, the temperature 0.8 centimeter from one phase. So, suppose this is one phase. So, 0.8 centimeter, total is 4 centimeter. So, 0.8 centimeter from one phase. So, this is say 0.08 centimeter, that is 0.008 meter, and from this phase it will be say 1.2 centimeter. The reason is 2L is given as 4 centimeter, this is equal to 0.04 meter, L is equal to 2 centimeter, which is equal to 0.02 meter, and the second part, that it is, this part is 0.8 centimeter, which is nothing but equal to 0.008 meter, and so from this side, from the center line, it is 1.2 centimeter. So, like that way, if we see that first part is A, where we have to find out center line temperature. For finding out the center line temperature, according to the figure, that it is basically a plot of TO by TI versus Fourier number for various 1 by Biot number. So, this is the case. Now, what we have to find out first, what is Biot number, what is Fourier number, that values we have to calculate. So, for Biot, it is we know that H into L by K, which is nothing but or this implies 1 by Biot, this is equal to K by H L, and this value is equal to 215 by 500 into 0.02, this is meter. So, this is becoming actually 21.5. So, Biot number, this is the unit dimensionless Biot number is 21.5, and the Fourier number is alpha T by L square. We know alpha is the thermal diffusivity and T is the time and L is the length, of which alpha is again K by rho Cp. K is the thermal conductivity, rho is the density, and Cp is the specific heat. So, if we calculate alpha for this aluminum, it is a property of the material. So, if we get it, then aluminum K value is being given as 215 again, and rho is 2700 kg per meter cube, and Cp, we have to be very careful to see the dimensions whether they are in all of in SI units and all, that we have to check, and we have to say that the things are becoming dimensionless. This is very important part. And then into your CP is 900. So, this keeps the value as 8.85 into 10 to the power minus 5 meter square per second. So, this is that thermal conductivity, and we know that thermal conductivity thermal diffusivity of aluminum is of the order of this kind, 10 to the minus 5 meter square per second. Okay. So, we get now Fourier number for this case is alpha is equal to 8.85 into 10 to the power minus 5. Now, the time is given for me is 60 second, that means 1 minute is being given. So, we have to put the time. So, by just putting the values of the time, we can find out the values of the center line temperature for various times. Okay, divided by the L square, and we know L is equal to 0.02. So, this is 0.02 whole square in this case, because 2L is equal to 0.04. So, L is equal to 0.02, and that way we get Fourier number as 13.28. And then what is left us is with us is that we can find out now the expression for or value of T naught by Ti from the figure, when Fourier number is 13.28 and Biot number is 1 by Biot is 21.5. So, these are the two important values that we have to see. Fourier number is this, and 1 by Biot number is 21.5. From that we can find out using the chart. Yes. So, we can see that for Fourier number is some are 13 point something, it is some are here. So, for some values of Fourier number around 13.28, we will go for the 1 by Biot number as 21, we will get a value, and from there we will try to get the value of Fourier number. T naught by Ti, this value T naught by T is coming around 0.55. So, just by using the chart we get from chart we find that T naught bar by Ti bar is equal to 0.55, nearly equal to, this is an approximation. So, then from there we know what is Ti bar. Ti bar is known to us as per the definition of the problem. It says Ti bar is equal to 400 minus 30, this is equal to 370 degree centigrade. Okay. So, we know Ti bar, then what is To bar? We can find out To bar is equal to 0.55 into 370, and that is equal to 203.5 degree centigrade, and then from there we can find out To is equal to T infinity plus 203.5 degree centigrade, and this is becoming 233.5 degree centigrade. So, this is the value of the center line, that is the first case. Now, we have to find out that case B, the problem B, part B of the problem. It says we have to find out that local temperature, any local temperature T for that distance 8 centimeter from the surface. That means here my L or x by L, we have a plot of for the chart T bar versus T over versus we have the plot is this versus 1 by Biot number when x by L is variable. That means, in this case x is equal to 1.2 as we have shown, that x 1.2 centimeter. So, x by L for this case is becoming 1.2 by 2 is equal to 0.6. So, for x by L is equal to 0.6, and already we have seen what is the expression for 1 by Biot number. 1 by Biot number is already we know that is equal to 21. 1 by Biot number is equal to 21.5. This value is also known to us. Then if we go for the chart as we have shown this, the next chart, this chart, we can find out for different Biot number. 1 by Biot number is about 21.5, and then x by L we have to go for a 0.6 curve, and then we can find out that the value is something coming very close to 1. So, T bar by T naught bar is nearly equal to 0.99, and we know what is the expression for T naught bar. So, we can find out T bar is equal to 0.99 into T naught bar is 203.5. So, this comes about 201.5 degree centigrade, and therefore, T equals to that any local temperature at that point x is equal to 1.2 or 0.8 centimeter from the surface as per the definition of the problem. T equals to 231.5 degree centigrade. So, one thing we can say here, that between these two results that we have got from A and B, that the temperatures are very close to each other, and possibly the reason we can understand it is that it is the case of aluminum metal, and which has got very high thermal conductivity. We can see the value of thermal conductivity is 2105 watt per meter per Kelvin. So, very high thermal conductivity allows the heat to be transferred in a very fast way, and so the resistance inside the body is very small. So, it is very close to a case of a lumped parameter model. So, one can even take care of even think of lumped parameter model for this kind of problems when the k value is very high, and we can see from the Biot number, which is 1 by Biot number is 21.5. So, Biot number is much lower than 0.1, which is the case we have seen that if Biot number is less than 0.1, then we may go for lumped parameter analysis, lumped parameter model, and solution is by lumped parameter method, and that case what happens is that estimated values remains within 5% error, that already we have discussed. So, therefore, as because K is very high for aluminum, so the resistance is very poor. So, we can see the difference in temperature at the center point and at a point 1.2 centimeter from the center point is very low, only by 2 degree centigrade, okay? and that is happening in 1 minute time. Now, the third part of the problem is the third part C of the problem. It wants to know that what is the heat flow rate from the slab. If we know that for this case we have a plot of Q by Qi versus Fourier into Biot square for various Biot number. Okay. So, we have already for this case we have already that Biot number is equal to 0.047. Already we have seen that 1 by Biot number is equal to 21.5. So, Biot is equal to 0.047, as I was telling that Biot number is very low, it is much lower than 0.1, and therefore, lumped parameter model is becoming applicable in this kind of cases. And we know that other part is Biot square into Fourier number, which is the x axis, and this is equal to, all the values are known to us. So, it is 0.047 whole square into Fourier number is 13.28. So, this gives me finally is 0.029. Okay. Now, once we know the values of Biot square into Fourier number, we know the value of Biot number, and then if we see the chart, yes, for different values of Biot number and for different for the values of Biot square into Fourier number in the log semi-log plot, we can find out Q by Qi is coming to be Q by Qi is coming to be 0.425. Okay. Now, we know what is Qi, that we can calculate. Qi is the initial energy content, internal energy content of the body, and with respect to the environmental condition, and that we know that Qi is equal to rho V Cp, that is the mCp into Ti bar by we have area. So, now V by A is nothing but for our case area, surface area into 2L is nothing but the volume of the sphere. So, V by A is nothing but 2L. In this case, V by A is equal to 2L. Okay. So, if we put this expression here, rho we know, 2700 and V by A is equal to 2 into L is equal to 0.02 and then Cp is 900 and then Ti bar is 370. So, we get this value to be 3.6 into 10 to the power 7 joule per meter square. So, we are getting the expression of Qi that in terms of per meter square, because that we do not know that surface area, because it is an infinitely long body. So, we do not know the exact surface area. So, we are doing it per unit surface area, and per unit surface area that Qi value is 3.6 into 10 to the power 7 joule per meter square, and we know that Q by Qi as 0.425. Okay. So, what we can find out from these, that what is Q? Q is equal to 0.425 into 3.6 into 10 to the power 7, and that value is becoming, now if we calculate, it is actually 1.53 into 10 to the power 7 joule per meter square, and this is equal to 1.53 into 10 to the power 4 kilojoule per meter square, or is equal to, you can say, 15.3 megajoule per meter square. Okay. Now, what is happening? We can see that we can calculate that this much amount of energy is being lost from the solid boundary. Now, the question is, we can see that the loss energy is about 42.5%, because Q by Qi is equal to 0.425. This is 42.5% of the initial internal energy for this case. Now, what we will do is, we will repeat this problem for the cases of a cylinder and the cases of a sphere. So, if we repeat the problem for, so problem 2 is, question 2, repeat the problem for an infinite cylinder of radius R O. Okay. So, now what we see here, that what are the differences that we try to find out? First thing is, if we consider this is the cylinder. So, the infinite cylinder means the cylinder is infinitely long, its radius is known to us, which is R O. So, if this is the center line distance, and so this is R O. Okay. And here this is H, here it is H, the heat is being convected out by to the environment, and here it is, say, T infinity, that is no. So, it is a convection boundary problem, again as we have seen in the previous cases. So, now the differences are with respect to the previous case is that here the surface area is a cylindrical coordinate system. So, surface area is different. So, if we say that V by A in this case is nothing but pi d L, any length L by A, the volume is pi R naught square into L by the area is 2 pi R naught into L. So, basically V by A is becoming R naught by 2, that is one thing. Then Biot number is expressed as H into R naught by K, that is in place of L it is R naught, and Fourier number is expressed as Fourier number is equal to alpha T by R naught square. Okay. So, these are the certain things that is just little bit changed, but fortunately that there are certain things are being unchanged. For example, we have told that so here the repeat the problem for infinite R and diameter is equal to 4 centimeter. So, that means the 2 R is equal to 4 centimeter and R naught is equal to 2 centimeter. So, thus what happens to our Biot number and Fourier number, they remains unchanged. So, Biot is equal to, as in the previous case, alpha t by r naught square. If we put the values, we will be getting again, it is remaining unchanged, it is remaining 13.28. Okay. And so 1 by, I am sorry, it is not Biot, this is Fourier number is remaining unchanged. Fourier number is equal to alpha t by r naught is equal to 13.28, and 1 by Biot is basically k by h r naught. This is also remaining unchanged because r naught is not changing, other things are constant. This is again the case, this is again a cylinder of aluminum. See, all the things are remaining the same because it is made of aluminum. All the physical properties, for example, physical properties here rho, k and Cp, this for aluminum remains the same as the previous problem we have seen. Yes, the previous problem, rho is 2700 kg per meter cube, k is equal to 215 watt per meter per Kelvin, and Cp is equal to 900 joule. And also the other part of the problem is maintained same, like temperature T infinity is equal to 30 degree centigrade here. Here the Ti is taken to be 400 degree centigrade, that is Ti, and also that H value is 500 watt per meter square per Kelvin. So, these are all maintained constant. So, under that situation, 1 by Biot number is becoming again 21.5. Okay. So, once we know this Biot number, once we know the Fourier number, now we can find out the values of T naught bar by Ti bar, and this is happening something around 0.275, and this we can calculate actually from, again if we go back to the plots, we will see that in case of cylinder, there is a plot of T naught bar by Ti bar versus Fourier number. For varies value of Fourier number around 13 point something, we can go for that line for 1 by bar 21.5, and from there if we try to find out the value of T naught bar by this thing Ti bar, it is coming around 0.275 roughly. So, it is about nearly equal to, I should say it is nearly equal to 0.275. Then what we are getting is that TO bar is equal to 0.275 again, and we know that Ti bar is remaining the same as we have done in previous cases, it is 370, and therefore, we get TO bar is equal to around 101.75 degree centigrade, and so TO, the center line temperature, is becoming 131.75 degree centigrade. So, this becomes the center line temperature. So, you can see the difference in the values with respect to the previous one, and once we know the center line temperature. So, this is the case A. Now, the case B for the same problem is to find out the local temperature, and for case B again exactly the similar method we have to find out T bar by T naught bar for this case, and again here also we will find out T naught by T naught bar, will T by T naught bar we have to find out for when there is a plot of this versus 1 by Biot number is the plot, and plot is this versus 1 by Biot number is the plot, and the variable is here r by r naught, and that is equal to again 1.2 by 2, and this is 0.6. So, again using the similar things, similar ways, we can find out that T bar by T naught bar is equal to nearly equal to, I should say, 0.98 here, and so we can find out that T bar as equal to 99.72 degree centigrade. From there we can write T is equal to 129.72 degree centigrade here. Also we are finding the difference is about 2 degrees, and as already we have discussed that this difference of 2 degrees is basically due to the reason of high thermal conductivity for the aluminum cylinder we have considered in the present case. Now, after we get the value of local temperature, then the part C, here again we have to find out the value of Q by Qi. From the figure we have to find out which versus Biot square into Fourier. So, all the values are known to you, Biot square into Fourier is same. exactly the same as we have done it for the previous case. I have intentionally taken up this problem just to illustrate this for 3 different geometries. What are the differences is lying to calculate or to consult with the charts and to get the values of the different parameters that is required by the problem. Okay. So, what we get, and in this case again the variable is the Biot number is the variable. For this case it is the variable. So, now we have again that Biot square into Fourier number, the value is 0.029, and from there we can find out that q by qi from the figure, it comes to be same the chart we have to consider, and from the chart we can get q by q I is equal to 0.7. That means, here in previous case we have seen that in case of slabs we have seen it is around 42.5%, and now we are seeing it is about 70% of the energy that is being lost if it is a cylindrical body of the dimensions being given. Now, what happens is, interestingly, the difference lies in calculation of the qi values here. Qi again it is rho Cp into V by A, that is the part, into Ti bar. So, the difference lies particularly only in V by A values, and we have seen the V by A is that we have already found out it should be equal to R naught by 2. In the previously we have found out that V by A is R naught by 2 is there in case of cylindrical coordinate system, and therefore, Qi is finally becoming 8.99 into 10 to the power 6 joule per meter square. So, if we put this expression over here, then Q is coming about 6.23 megajoule per meter square. So, this is the third part, that this much amount of energy is being lost in 1 minute duration. The duration has been 1 minute. Okay. Now, the same problem will repeat. So, we will say it to be problem 3. We will repeat the same problem for a sphere of diameter 4 centimeter. So, we have intentionally kept the diameter of this sphere is same again as the cylinder, just to have all other parameters remaining more or less the same. So, we have a this is the sphere here, and this is the center line, this is the center line, and basically this is your R naught is the radius of the sphere, and this is the convecting environment. This is already as per the problem, as initially it is stated, it is 500 watt per meter square per Kelvin, that is the heat transfer, convective heat transfer coefficient, and diameter is known to us, that 2 r, if we say that 2 r naught is equal to 4 centimeter, that is known to us, and then only this is diameter, okay, r naught, and then what is there is that here if we try to see that V by A, and that is becoming 4/3 pi r naught cube by 4 pi r naught square. This says that V by A is equal to r naught by 3. So, this is a interesting difference with respect to the previous things, that V by A values is different. Otherwise, if we see for part A, we have to find out the dimensionless center line temperature. It is again that you have T naught bar versus T I bar, and this is same here. It is T infinity is 30 degree centigrade, and here T I is equal to 400 degree centigrade. Okay. These are known to us, and we have the plot of T O bar versus T I bar, T O bar by T I bar versus we have a plot of Fourier number for various 1 by Biot number. And here also we see that Fourier is again we will say that alpha t by r naught square, and again the value remains the same. In case of sphere, the value remains the same as 13.8 28, and Biot number also will be expressing again k by h into R naught, where k and k is same, alpha is same, because all the things are again the property of aluminum. This is made of aluminum, the sphere. So, the property of aluminum is there. So, these values are same. So, we can get 1 by Biot is equal to k by h R naught, and that value is becoming again 21.5. And so, once we know the values here, once we know the values of 1 by Biot, we can find out T naught bar by T I bar, and that is equal to here. Interestingly, this factor is becoming 0.17. So, we can see that gradually the things are becoming reduced, and then we know that T O bar is becoming 59 degree centigrade, and then we can find out T O is equal to 89 degree centigrade. So, we can get the central line temperature as 89 degree centigrade for this case. Okay. Now, we can see that gradually the temperatures are, for depending upon the geometry, the temperatures are gradually decreasing. And then if we go for part 2 of the problem, where we said that we have to find out that this is the sphere, we have to find out at certain distance, this is 0.8 centimeter. So, basically from here the R is becoming again 0. Sorry, I'm sorry. So, actually if this is the sphere, so we said that around 0. This value is 0.8 centimeter, and this R is then if this is R, then R will be equal to 2 centimeter minus 0.8 centimeter. So, this is equal to 1.2 centimeter. So, it remains the same as we have done for previous cases, and then what we will find out is that for part B it is T bar by T naught bar we have to get versus the plot of, from the plot of this versus Biot 1 by Biot number, and we have to get for various R by R naught, and in this case the R by R naught is equal to again 0.6. Okay, that is maintained, and then all other things are known. So, we can find out T bar is equal to again nearly equal to 0.98 into 59, and so T is becoming 87.8 degree centigrade. So, we have seen that T naught has been 89 and it is becoming 87.8. So, very close to each other, again the same logic that K is very high for that thing is happening. Now, come to the part 3 of this, that Q by Qi. In this case we have to, this value is coming to be around 0.83 from the chart, and we know that here that Qi is to be found out is equal to again rho Cp into V by A. This is the difference, V by A into Ti bar, and this is equal to 2700 into Cp we know something around 900, and the V by A is R0 by 3, and we know Ti bar what is the value, and this Qi is coming around 5.99 into 10 to the power 6 joule per meter square, and so if we put the value, then we get Q to be 4.98 megajoule. I am sorry, it is megajoule per meter square. So, we see that this is the heat loss from the spherical system, and from the spherical body the heat loss is about 83% of the original heat content, initial internal energy content, 83% of that is getting lost in 1 minute. So, heat loss from the spherical body is the maximum per unit area. So, this is everything is we are discussing per unit area. Okay. Now, this way we have tried to explain that utilization application of the various charts for finding out the solution to unsteady state heat conduction problems, particularly for distributed parameter model systems problems. Okay. In fact, apart from these things, whatever we have discussed, that there are analytical solutions possible. As analytical solutions we have discussed by separation of variable methods, analytical solutions we have discussed by combination of variables method, developing a new variable. Similarly, analytical solutions of the partial differential equations could also be possible. There are several other ways, like just by taking transforms like Laplace transform or Fourier transform that can be used to sometimes to get a solution of the analytical solution of conductive unsteady state conductive heat transfer problems. At the same time, there are another way by which that heat conduction problems, unsteady state complicated heat transfer problems can be solved. That is called by numerical methods. So, using numerical methods, the partial differential equations which will be obtained, that has to be first discretized with the help of finite difference method or finite element method, and then one can find out through computation they can find out that the desired values of the temperatures at different locations of the solid body. In fact, that is beyond the scope of this particular course. So, therefore, we are not discussing in details on that part. So, numerical methods is a useful tool. We all know a numerical method is a useful tool for solution of differential equations which are not possible to be solved by or simply by analytical method, or the problems solution is very complicated, and under those situations numerical methods are used. So, if the students when they will be learning some mathematics course, they might be knowing the part of the numerical methods, and then they can apply in their as an application to the mathematics courses. They can take up this kind of heat transfer problems, conductive heat transfer problems, unsteady state conductive heat transfer problems, or multidimensional heat transfer problems, which are more and more complicated things, and try to find out the numerical solution to these through discretization of the solid body by using finite difference method or finite element methods. However, so this is through this lecture we would like to complete the conduction phenomena of heat transfer. Now, next class onwards we will be discussing about the convection, where the conduction will also be there, but the convection is the major thrust. So, convective heat transfer we will be discussing from next lecture onwards. Thank you very much.